In this lesson, we're going to be applying areas under a curve into kinematics. We've already seen that the area under a curve, so if I have a curve over the interval AB, for which I need to determine the area under that curve, I would find that area by integrating the absolute value of f of x over that interval, if this is the curve of f of x. However, we do know that the velocity is in fact the derivative of the displacement. So naturally, in order to determine the displacement of a particle or whatever object that is moving, it is natural to in fact integrate the velocity. However, if I do have the velocity graphed against time, which by the way, the velocity against time could also be negative. The curve could be below the x-axis. So in order to find the total distance traveled between A and B, what I would need to do is determine the area under the curve of the velocity. So that is why the total distance traveled between 2 times t1 and t2 is in fact the integral from t1 to t2 of the absolute value of v of t. So before I jump into integrating the velocity, I need to study the sign of v of t over that interval, which means I need to study the relative position of the curve of the velocity with respect to the horizontal axis or the time axis in this case. So in this example, we have a particle that is moving such that its velocity at any time t can be modeled by the curve t minus t cubed, and that is in meters per second. And I need to find the total distance traveled by the particle after 2 seconds. Now, usually the total distance traveled is in fact given between two given times. And over here, saying after 2 seconds, it means that it's starting from the moment where the particle started moving until 2 seconds later. So over here, that is in fact between t equals to 0 and t equals 2. So I need to determine the sign of this function over the interval 0, 2. Now, so what I need to do is first start by setting up a table of signs of v of t. To set up a table of signs, I need to first start by determining the roots of the function in order to know if at any moment over this interval the curve changes signs, because the curve changes signs around its x-intercepts. Okay, so over here that's t into 1 minus t squared equals to 0. So that is t equals to 0, or t squared equals to 1, which gives me t equals to 1 or t equals to negative 1. So now that I have the roots of v of t, I need to in fact start by setting up a table of signs. Now v of t consists of two factors. The first one is t, the second one is 1 minus t squared, and their product is what in fact gives me v of t. So I start by setting up the roots on the number line I have for the first row. So it's negative 1, 0, 1. So t, the first factor, is 0 at t equals to 0, and that would also be a root of v of t. And then negative 1 and 1 are roots of the quadratic factor, and they're also a root of the velocity. So let's just start by distributing the signs for each factor. So t is negative before 0 and positive after 0. Now over here, of course, naturally t is time. So t starts from t equals to 0. The domain is 0, positive, infinity. However, over here, I'm just setting up the table of signs in general. Just maybe in some other context, you needed a negative domain. Okay, so now we're going to restrict our domain in a bit. But I'm first setting up the table of signs over all r, just in case you needed to do so in another context. Now 1 minus t squared. 1 minus t squared, that's a quadratic function with two roots. So between the roots, it would have the opposite sign of a, where a is the leading coefficient. Here, the coefficient of t squared is negative, so between the two roots, it's positive. Outside the two roots, it's negative. So multiplying the signs, I would have between negative infinity and negative 1, v of t to be positive, between negative 1 and 0, v of t to be negative, between 0 and 1, positive, and between 1 and positive infinity, it's negative. However, as I've just mentioned, that t is in fact greater or equals to 0. So this is what I need to look for, in fact, this part of the table of signs. So I need the total distance traveled by the particle after 2 seconds. Now this is where I have t equals, sorry about that, this is where I have t equals to 2, because don't forget that this goes all the way to positive infinity. However, I'm only interested with the interval 0, 2. So as you can see, over the interval 0, 2, the velocity does change sign at x equals or t equals to 1. So between 0 and 1, the velocity is positive, and between 1 and 2, the velocity is negative. So the total distance traveled that we're looking for is in fact the integral from 0 to 1 of v of t. So that is t minus t cubed dt, while between 1 and 2, the velocity being negative, then it's minus the integral from 1 to 2 of the velocity. That is because the total distance traveled is in fact the absolute value of the function over that interval. So over here I have half t squared, we're integrating with respect to t, minus 1 over 4 t to the 4 between 0 and 1, minus half t squared minus 1 over 4 t to the 4 between 1 and 2. Now, evaluating upper bound minus lower bound for each, that would in fact give me half minus 1 over 4, that is for the upper bound, and for the lower bound it is a 0. However, for the second one, for the upper bound, it's a 4 over 2, which is a 2, minus 16 over 4, which is a 4, that is for the upper bound, minus, you'd notice I grouped them so that all of this would be multiplied by this negative. And for x or t equals to 1, it's half minus 1 over 4. Okay, so you'd see half minus 1 over 4 is in fact a 1 over 4 plus a 1 over 4, that is a half. So I do have a half minus 2, so that is a half plus 2, so that is a 5 over 2 meters, that's in meters, or a 2.5 meters, because the distance here is given in meters.